Okay, so for example 10.6, we're asked that an electric motor exerts a constant torque of 10 newtons by meters on a ground stone mounted on its shaft. The moment of inertia is 2 kilograms by meter squared. If the system starts from rest, find the work done by the motor in 8 seconds and the kinetic energy at the end of this time. What was the average power delivered by the motor? So they're asking us to find the work, the kinetic energy, and average power. Okay, so to find these things, we know that work is going to be equal to the the torque time sorry, hold on a moment. Pretty sure it's the torque times the change in angular, or the torque times angular displacement. That's what this is, right? Okay, so in order to find, we don't really have angular displacement, but we're going to use this equation here to help us find angular displacement. So we know that the torque is equal to the moment of inertia times alpha. So now if we solve for alpha, we know it's alpha is going to be equal torque divided by the moment of inertia, and we have that's going to be 10 over 2 given to us by the problem. That's going to be equal to 5 radians s squared. That's alpha. And to find the change in the angular displacement, it's gonna be the initial plus the work done and times the torque. Now this should all be zero, so this should all be zero, and we're actually missing a part. Let me write it in. It should actually just be plus half of the alpha plus t, or sorry, no, just t squared, right? And what we're really writing is just this section, because this is all zero. So then we get half of 5 times the second 8 seconds squared, right? The alpha is 5, which we got here before, and we get 160 radians right here. Now we plug in those 160 radians to the work formula, which we have here before. The 160 radians is the angular displacement, right? So, and we have the torque. The torque. So work is going to be equal to torque times 160, and that's going to give us 1600 joules, and that's going to be equal to the work. And the 1600 joules should be, it's also the kinetic energy at the final kinetic energy. So that it's both work and final kinetic energy. And to find the average power, it's work divided by the change in time. It's going to be 1600 joules we got before, divided by the 8 seconds, and it's going to be equal to 200 watts. And that's going to be our average power. And you can check to see if the kinetic energy is the same. It's 1600 joules, and you'll see it's the same. You check by doing half times, by finding the angular velocity, and then you multiply that by half, and then by the moment of inertia, and you should get 1600 joules. Okay, and that's all.